Hello everyone, in this video we're going to learn about significant figures and how to properly use them. Assume you need to measure the length of your wallet and you have two rulers to do so. If you use the ruler on top, you will get a less accurate reading because the ruler in the bottom has the finer graduations. If you use the ruler on top, you can definitely see that the reading lands between 5 and 6, but you'll have to estimate the second digit. If you use the ruler in the bottom, you can definitely see that the reading lies between 5.3 and 5.4, and you have to estimate the third digits. So the more accurate your measuring device, the more significant figures you have. Because both of these readings are comprised of non-zero digits, it's easy to say that the measuring on top has two significant figures and the reading in the bottom has three. But because there's sometimes zeros involved, it might be a little challenging to count the proper significant figures if you're not familiar with the rules. And the rules are as follows. All non-zero digits and zeros that are sandwiched between them are considered significant figures. Zeros that come before a non-zero digit do not count as significant figures, but zeros that come after a decimal point and after a non-zero digit do count as significant figures. That's why 0.200 has three significant figures. On the other hand, zeros that do come after a non-zero digit but are not followed by a decimal point do not count as significant figures. That's why 190, despite having three digits, only has two significant figures. So if you want those zeros to count, the zeros that are telling a non-zero digit, you have to punctuate them with a decimal point. So 190 plus a decimal point has now three significant figures. So let us test ourselves by determining the significant figures that each number carries here. Number one has three non-zero digits, so three significant figures. Number two has 1 followed by 4 zeros followed by no decimal point, so only 1 counts as the significant figures. The rest of zeros do not count. Number 3 is an easy one. It's non-zeros and a zero sandwiched between a non-zero, so that will count it to 5. 4 is reported in scientific notation, so you don't count the tens and the exponents of 10. So it's the intended value, it's the meat of the value that carries the significant figures. 6.060 has 4 significant figures. Why? Well, the first zero is sandwiched between two non-zero units, so that counts. And the second zero comes after a non-zero digit and after a decimal point, so that does also count as significant figures. Number 5 has only 1 significant figure. Why? Because all those zeros are coming before a non-zero digit. Number 6, again, is a scientific notation. So we only count the zeros. We only count the significant figures in 5.4456, and those are all non-zero, so that's 4. 5050 or 5050, example number 7. The first zero is sandwiched between two 5s, so does that count? But the second one does not because it's not followed the decimal point, so that has 3 significant figures. 8 has 5 significant figures, right? Now, the first zero still counts. The second zero is now followed by a decimal point, and the third zero is coming after a non-zero digit and after a decimal point, so it does count. All of those zeros count. 6.8 has 2 significant figures, and 0.02110. The only zero that counts as a significant figure is the terminal zero in example number 10, because all the other zeros are coming before a non-zero digit, which does not make them significant figures. So 4 sig figs is the total significant figure count. Now, let's discuss the 4 main actions involving significant figures. What if your components of a subtraction or addition or multiplication are numbers with different accuracies? For example, in example number 1 on the action addition and subtraction side, we have 4.03 and 5.4. One has 3 sig figs, the other one has 2. Same for the other example. So what is the procedure? Well, you must know that addition and subtraction have slightly different rules than multiplication and division. In addition and subtraction, the final response should have as many digits to the right of the decimal point as your least accurate component. For example, in question number 1, 4.03 has 3 sig figs and only 2 digits to the right of the decimal point. But 5.4 has two significant figures and only one digit to the right of the decimal point. So your final response has to be rounded up or down to have only one digit to the right of the decimal point. So your raw response might be 9.43, but it's only allowed to have one digit to the right of the decimal point because 5.4 has only one. So 9.4 would be the final response. In multiplication and division, the story is different. In multiplication and division, the final response should have as many significant figures as your least accurate component. In example number 1, 5.68 times 10. 5.68 has 3 sig figs, but 10 has only one. So for your final response should only have one significant figures. So the raw response is 56.8. You'll have to round it up to 60 in order to house only one significant figure. Let's practice these rules in some examples. Example number 1 is an addition. 35.6 has only one digit to the right of the decimal point. So your final response has to be of proportion. So final response only has to have one digit to the right of the decimal point. So 91.9 would be the final response. Second one, again, it's addition. So the final response would have to have the least amount of digits to the right of the decimal point, which would be 3. Same with number 3. 4 would have 2. And so on and so forth. Let's discuss scientific notation. What is scientific notation? It's a contract between all scientists to report numbers, no matter how small or big, are in the same fashion. So in scientific notation, you have the coefficient that is only allowed to have one digit to the left of the decimal point, and then the rest is compensated with the base of 10 and the exponent. What is important about it is that the scientific notation has to have the same number of significant figures as the intended value. 450,000 has 2 sig figs, so the scientific notation should carry that. 0.005453 has 3 sig figs, so the scientific notation should carry that. Some examples: 500 has 1 sig fig, so the scientific notation for it has only 1 sig fig. 7,700,000,000 has 2 sig figs. Scientific notation should follow. And the third value has only 2 sig figs, so the scientific notation should reflect that as well. Let's do a scientific notation sample together. The intended value is a small number. We want to move the goalpost, which is the decimal point, for the orders of magnitude to the left, 4 places to the left. So we are aggrandizing that molecule by a factor of 4, which has to be compensated with the exponents of 10. So 2.65 times 10 to negative 4 is the same as 0.000265, but that's the proper scientific notation. And pay attention that you have 3 sig figs in the intended value, and you have 3 sig figs in the scientific notation. If you want to test yourself with scientific notations, you can do the following question. Remember, the answer to these questions could be found at the end of every slide.